How's it going, everybody? In this video, we're going to take a look at our next EIGRP topic, which is going to be scalability. Scalability is got multiple subtopics, if you will, when it comes to how EIGRP does its job and things like that. And we're going to talk at a high level initially about some of the different characteristics and capabilities that EIGRP supports in terms of scalability. Most notably, we'll talk about stub routing, we'll talk about summarization, and we'll talk about leak maps and how those come into play. We're not going to dive into those immediately. I'm going to spend a little bit of time explaining how scalability comes into play and how scalability and convergence really join together, because they're really important topics that if you are just getting into EIGRP and you've learned a little bit about EIGRP up to this point, you need to know a little bit more of the theory and how it's applicable to an EIGRP infrastructure versus just typing the commands into the keyboard and affecting the way that EIGRP forwards traffic. Because once you do that, then and you have the theoretical understanding, then you can pretty much map that understanding to any scenario, and you'll be like, okay, I can do this, and this, and you'll be in really good shape. So let's go ahead and dive into those details. So I'm going to do a little bit of whiteboarding initially, and we're going to take a look at how all this stuff comes into play, because it's really important that we understand these details. So the first thing that we're going to understand is the sub-second convergence option that EIGRP supports. So we took a look at this in the previous video where we talked about you have successor and you have feasible successor, right? So obviously primary and backup respectively. That means, let me go make this a little bit bigger so you guys can see this. So from router 5's perspective, he knows about router 1's loopback address, and because we've enabled EIGRP on all interfaces, we can go this way to get to there, we can go this way to get to there, and we also have this way to get to there, right? So we have three different possible ways to get to where we need to go. Now, this way here, number 1 and number 2, are going to be immediately available to router 5. This one right here, which is technically our third, isn't immediately available to us because of the fact that we've only got 2 physical links. So your reconvergence will always be limited to the amount of circuits that are physically attached to you, that you have reachability to other nodes that are running EIGRP. So to put this in layman's terms, if I have a way of going this way and a way of going this way, those are my only 2 ways to get to wherever I need to go. Now, when we get to router 6, we can only go this direction because we can't go back the way we came, because then that would institute a loop, and that's not going to work. Same thing with router 4. We can't go back, right? That won't work this way. We can't go back towards router 5. That won't work. So we have a couple of options. On router 4, I can either go this way or I can go this way. How does it determine that? Again, composite metric. It looks at what XR3 and XR2 have advertised to it, and it makes a determination that way. Because remember, each node in the EIGRP domain has its own view of the network and will take that into consideration. So even though we have multiple ways of getting from point A to point B, we can't go that route unless there is a loop-free viable path to allow us to do that. So in the event that we run into a scenario where this is my primary path, for example, right? Let's say this is primary, and then this path right here is backup for whatever reason. And then we have a tertiary connection, but not physically attached to us. We have this path here that we can take to go from router 4 in the event that we need to. Now you might say, well, what about with the path with router 6 towards XR3? Well, theoretically speaking, we could go this way, but as you can see, the more ways we look at it increases our number of nodes we have to pass through, the more transit links that we have to go through, the more transit nodes we have to pass through, so on and so forth. So those are just not viable solutions. So we're going to remove those 2. So we have our primary, we have our backup. In the event that this guy goes down, what's going to end up happening? Well, we have a backup path, right? So because we have a backup path, if this one's the primary and he goes away, is EIGRP going to ask anybody else what's going on? It doesn't need to, because it already has a pre-calculated backup path that can immediately insert into the routing table. Now let's talk a little bit about the tables. We didn't talk about the tables in the previous video because I wanted to help you understand how convergence and scalability are going to help move those table information in those tables back and forth. You have three tables. You have the neighbor table, you have the topology table, and then you have the routing table. What is the neighbor table? The neighbor table is any connections that you have between a couple of nodes. This is the neighbor table. Okay? Who am I peered with? Who are my neighbors? Things like that. The topology table is what are the connected interfaces on these particular devices that are enabled to run EIGRP. So in this case here, for example, router 1 has 1, 2, and then a loopback, 3 connected interfaces to it. So my topology table, I would have, for router 1, I'd have 1, 2, 3 routes that are going to be learned from router 1 that are going to be in my topology table, no matter where I'm at in the EIGRP domain. Only one of those, or I'm sorry, all 3 of these can be inside of the routing table, but how they are inserted is based off of who I'm peered to and what the lowest composite metric is for each neighbor to reach the destination networks that I'm trying to get to. In other words, if I'm on router 4 and I want to get to router 1's loopback address, I have 2 different ways that I can go about getting there. So how do I do that? Well, I can either go towards XR3 and then to R1, or I can go XR2 to R1. But I have equal cost paths. So what do? I actually take, and because of the fact that I've got 2 ways of getting there, 1 for each neighbor, I would install the route twice. So I would install route 1, 2, and 3 twice. So, and I would go XR3, XR2, XR3, XR2, XR3, XR2, right? Because I have multiple ways of getting to the same destination multiple times. And that's where this backup path process comes into play. As long as I already have a pre-calculated backup path, convergence is actually really, really fast, because then what I'm doing is I'm taking any routes that are in the topology table that are not already in the routing table, and I'm just simply inserting them into the routing table. And it takes milliseconds to do that versus having to go figure it out. So what happens if I don't have a pre-calculated backup path for whatever reason? What happens if a link is down for whatever reason? Let's say for kicks and giggles that this link is down and I need to go this way to get, this is my only path, but this link goes down. What do I got to do? And there's no pre-calculated backup path. What do I have to accomplish? Well, the first thing that's going to end up happening is a query. Now, a query is simply what that means. It's a question. So what will end up happening is when a router detects the loss of a network that it had reachability towards, that is now gone, the router is going to go, hey, I need to figure out if anybody else has an alternative path to that same destination via a different path. So what will end up happening is if this thing goes down, XR3 will send a query out this way, and this router will get it. He'll get the query. So and this guy will get a query, and they'll be like, do you know how to reach, say, router 1's loopback? And if they do, then they'll send a reply back with that information. If they don't, they'll send a reply back with that information with negative. Actually, let me change the color real quick on that. If they have a reply with good information, they'll reply with that update. If they don't, they will also reply, but with a negative response saying, no, I don't. Same thing with this guy. Let's say he doesn't have a reply either. He doesn't know what to do. So he's like, nope, sorry, you don't have an alternative path. So what ends up happening? Well, the route is removed. So we pretend like we don't have that loopback address. So, loopback 0 for R1 is now gone bye-bye. It's no longer there. And that's one of those things where you have to understand that process. Now, what happens if you send a query out or you lose the loopback address? So let's say we shut down the interface, but none of the links are down. What ends up happening then? Well, same thing. We're going to actually send on router 1 if a link goes down for some reason. There's another scalability process that comes into play known as poison reverse. What will end up happening is router 1 will send a link or a message to every one of its out to any of its neighbors, stating that this link is dead. This loopback address, done. You can't reach this, so remove it from your routing tables. And then he'll send it this way, 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 he'll send it that way, so on and so forth. You can see the propagation comes into play. Now, because of all that information being sent, now we have to synchronize. It's not like OSPF where all the databases get synchronized, but now we have up-to-date information. But in the event that you send a query out, you send it out every neighbor that's active that you have. So you're going to send the query out everywhere and hoping that somebody will respond. Now, if you don't respond to the query, then there's a couple of timer values that come into play. Whenever a link goes active, it moves from the passive state, which means converged, understood, known about, to active, or I don't know how to get there, I don't know where to go, can you help me out? Be no different than if you're traveling somewhere and you don't know exactly where you're supposed to be going. You can stop at the local gas station and be like, hey, how do I get to XYZ destination? And they might tell you, or how do I get to the interstate? Or where do I go for this? And they can point you in the right direction. So they can reply to your query and give you point you in the right direction. If it's active, you're sending out queries. Queries are being sent everywhere in the network. So active means queries are being sent. What should end up happening in a properly designed EIGRP environment is you should receive replies back in. The replies are going to say, hey, everything is good, this is what's going on, or no, I don't have any information for you, so sorry to tell you that you're kind of out of luck. So in the event that happens, then in a normal environment, the query will come back pretty rapidly and you'll simply be able to remove the route. But if you wait too long, this active timer will eventually expire without a query reply, and you go into what they call SIA, or stuck inactive. If you go into stuck inactive, that's a bad thing. Normally, if you go into a stuck inactive, you have a scenario where traffic is taking too long to get back to you, and that's a problem. There are ways to mitigate that. I have never seen that in production personally, but I've heard some horror stories where stuck inactives come into play with improperly or too largely scaled EIGRP environments, and you have to take that into consideration. But just remember, that's basically how this process all comes into play. So that's basically how, if you lose a neighbor, that's how everything is figured out and stuff like that comes into play. Now, there's a couple of different things that you can do with the query domain itself. You can control how big it is and how far it extends and things like that. So the way that you control that with the summarization or with the query, the first one is going to be summarization. It's not in any particular order. Summary, you have stub, and then you have filtering, and then you have multiple processes or multiple autonomous systems. These three right here are pretty easy to roll out. A summary is exactly the way it sounds. You're taking a or if you don't know what this is, you're taking a group of advertisements, so a group of prefixes, a bunch of /24s, for example. Maybe you've got 10 /24s. If you've got 10 /24s that you're advertising, you could summarize these 10 /24s into one shorter match, like a /24, or sorry, a /22, or a /21, or something along those lines. And we'll talk about how summarization comes into play here in just a minute. Stub routing is a unique way of basically telling, you configure this on like any router you want to. And normally you're going to configure this on a router that connects down to LAN segments. So for example, let me go ahead and clear the screen off, and let me come down here to the bottom so it's a little easier to whiteboard this. So again, we have summary, we have stub routing, or stub, we have filtering, and then we have multi AS. Again, summary, and the cool thing is with summary, you can summarize anywhere. So anywhere this can be done. Stub routing, if I have an environment like this where I've got something like this set up, and I have maybe an iNet connection here that goes out to the internet, and then this one over here, I have MPLS over here. I can have LAN segments hanging off of this guy, and then I can have EIGRP adjacencies between these guys and these guys and these guys, and everybody will be happy. And what I can do is I can basically say, turn this guy into a stub. A stub basically means there are no routers sitting this way or this way. The only two people, or only two routers that I'm peering with are you guys. All I have attached to me are LAN segments or end users. So you could have servers, or you could have PCs or printers, or whatever other type of scenario you might be running into. A stub effectively is going to say, I'm not connected to anybody that you need to know about. I'm literally the end of the EIGRP domain. I only have end users connecting to me. Therefore, it doesn't make any sense for you to send me a query. There's no reason for me to respond to the query. I'm going to go ahead and let you know not to send me query messages. That's stub routing. Now, there's about a half a dozen or so ways to modify that, and we'll take a look at those a little bit later on. But that's basically how that works. The last one is going to be filtering. Filtering allows me to control what I send and what routes I will actually limit and things like that. When I do traffic engineering with that, and when I deal with filtering, I have to be careful with that because there are a handful of scenarios where I could accidentally black hole traffic, which kind of ties into the summarization component. But when I talk about the filtering piece, there's probably a dozen ways that you can filter. I mean, it's not actually a dozen, it's more like 7 or 8. But if I'm running into a scenario with filtering, I am basically not advertising a prefix to you, so therefore you have no reason to assume that I would have reachability towards it. So an example of that would be if I have R1, R2, R3, and R4, and I have a bunch of LAN segments hanging off of this guy, and he's doing his thing, he's connected to R2 and R3, so on and so forth. I have a topology built like this. If I go to R4 and I do some sort of filtering where I say, you know what, this LAN segment right here, I'm not going to advertise it out. This LAN segment doesn't get sent. If this LAN segment doesn't get sent, therefore, if R1 would never learn about it, therefore he would never know to query for it, so on and so forth. That's basically how that comes into play. So that's basically how this comes into play. There's not a ton in terms of scalability that you need to be concerned with. There are a couple of use cases that you would need to understand, but beyond that, that's pretty much where we sit. The last one here is multiple autonomous systems. So with multi-AS, I might have R1, R2, and R3. And let's say I have a segment sitting between these two. Let's say I split R2 in half, and on the left-hand side here I use AS20 or 12, and then over here on the right I use AS23. Now, if I've got LAN segments hanging off of each one of these, for example, like that, and they're being advertised into EIGRP, so let's say I've got LAN segment 1 and 2, and this guy's got 3 and 4, respectively. Then R1 in this one, or I'm sorry, R2 here will learn about LAN segment 1 and 2. R2 will learn about an AS23, 3, and 4. However, R1 and R3 will not learn about each other's, or nor will R2 exchange the information. If I want to do multiple ASs, this guy right here, this logical line in the sand, is where the queries stop, and that's as far as they will go. If I want to release that information between each other, I would have to do mutual redistribution AS to AS. So I would have to allow 23 into 12, and I'd have to allow 12 into 23. By doing that, then I would see 3 and 4 here, as well as 1 and 2 here, and then you'd see since 1 and 2 are connected, you'd see 3 and 4 added, and over here you'd see 1 and 2 added, and then they would have reachability to each other. So that's basically how multiple ASs would work. Rare to see that, but in more designs, a great example of how you would use multiple ASs to do the job, as well as potentially summaries, is right up here where we would be doing things like DMVPN. So let's say, for instance, this is the HQ site, and then we have hub 1 and we have hub 2. What I can do is I can have this as EIGRP AS 100, right? Or let's do 110. And then I can have, that would be this AS, right? And then I can have a tunnel to 45, and I can have a tunnel to 46, and I can have a tunnel this way and a tunnel this way, right? I can have this set up this way. And then I can have all of this is AS 75, for example. And then over here, I can put these guys in their own AS and these guys in their own AS, and this would be like 103, and this would be 104. And you just have to do redistribution between the ASs. And by doing that, they would be able to learn the information back and forth and get everything squared away that they need to. So that's just an example of how that would come into play. Well, we can demonstrate that when we get into a little bit further along. There's some stuff that I'm not going to show you right away because we're not ready to really demonstrate those advanced capabilities, and this would be a perfect use case for that. I've actually done this a few times in production because I needed to in order to scale the network the way that I need to. Now, you end up getting a lot of EIGRP external routes in your network. There's nothing wrong with that, but in the event, because EIGRP external routes have an AD of 170, you potentially could be learning EIGRP routes that have a lower AD, like 90, which is the default, being learned another path. Well, you might have an out-of-band connection, or like a dark fiber, or a different link to another destination, or to the destination you're advertising over DMVPN. You might have an alternative path this way that I don't know about, and that I would have to know about that in order to circumnavigate or mitigate a situation where you are advertising these links right here into that was weird, where you're taking these links right here and you're advertising them this way as here, so that when iOS 46 receives it, he's learning them via two different ways, but he's going to prefer the internal EIGRP versus external EIGRP because of the simply the administrative distance. So these are some things that you need to take into consideration when you're focusing on this stuff, because if you accidentally have an alternative way of getting to a particular destination, that could change the routing scheme and how things are happening. So just some things to be aware of in terms of the operations and things like that. We will be taking a look at a couple of examples in the next video. I wanted to cover at least the theory here, and then we're going to start knocking out summarization. We'll take a look at stub routing, and we'll spend some time on filtering, and then when we get to EIGRP or DMVPN, FlexVPN, that type of stuff, we'll take a look at doing multiple autonomous systems and how that would come into play, and how that would, you could mitigate the propagation of queries. We're not going to be spending a ton of time focusing on reconvergence, simply for the fact that, well, I could come up with a couple of examples, but at the end of the day, I just understand the process, and then I will do my best to show you what I've learned to be the best way to deploy EIGRP in different scenarios and things to steer away from so that you don't run into those problems. So with that being said, that is pretty much it for this video. If you have any questions, please leave a comment in the comment section below. Please like, share, and subscribe, and I'll catch all of you in the next video.